Welcome to Study Loop.
Okay, so we're doing chapter 29, problem number 9. So this problem says there's a circular loop of flexible iron wire has an initial circumference of 165 centimeters. Okay, but it's decreasing at a constant rate of 12 centimeters per second. So dc dt is negative 12.0 centimeters per second. And a loop is in a constant uniform magnetic field oriented perpendicular to the plane of the loop with magnitude of 0.5 teslas. Okay, so it means we have a B field into the page, which we will call, and so B field, and we'll call that positive direction, 0.5 teslas. We'll say that's positive Z direction. Okay, into the page is positive Z direction. So into page. Okay, so now we want to find the EMF induced in the loop at the instant when 9 seconds have passed. Okay, so let's find the magnitude of this using Faraday's law. So Faraday's law says this is given as the change in magnetic flux, the change in time. So since the magnetic field is not changing, our flux is given as the B field out of A, but our A is changing. So this as a function of time, we can express it in terms of the circumference, right? So this is pi r squared, but r is circumference over 2 pi. So this is the same as circumference squared over 4 pi. So this as a function of time is now given as b, the magnitude of b, times c as a function of time squared all over 4 pi. Awesome. So now, since we know this, we can take the derivative. So d phi dt. Using implicit differentiation here, we have left with b over 4 pi, our constants, and since this is c of t squared, this comes down to 2 c of t dc dt. So this becomes bc over 2 pi dc dt. So our magnitude of our EMF then is now b over 2 pi times c times magnitude of dc dt. And we know all these values, so we can just plug these in. Or first, I guess we got to find what is c at 9 seconds. Okay, so c at 9 seconds is 165 centimeters minus 9 times 12 centimeters per second, because that's the rate. So this becomes 57 centimeters. So let's calculate this now. We have 0.5 Tesla over 2 pi times 57 centimeters times 12 centimeters per second. So if we plug this all in SI units, we see it comes out to 5.44 millivolts. Cool. So now let's do part B over here. So B asks, find the direction of the induced current in the loop as viewed looking along the direction of the magnetic field. Okay, so if we're looking on the direction of the magnetic field, the positive flux is decreasing in magnitude. So that means our flux is decreasing in magnitude. So we want a induced current that's going to be increasing to oppose this decrease, which means by the right hand rule, we need the current to be pointing in the same direction as B. Since B is decreasing, we want it to point in the direction of B. So that means we need a current induced to be into the page, right? Okay, so if the induced current needs to be into the page, using the right-hand rule, we see that that must be oriented counterclockwise. Oh, sorry, that was obvious wrong. That is clockwise. Check your right-hand rule again. If this is our loop, if we want it to be into the page, this has to be clockwise using the right-hand rule. So the current induced is clockwise.